little bit, but yeah, I've been looking at neural networks a little bit. First thing, question is, what are neural networks? And I guess it's an architecture for a computer, either a hardware or software architecture. And basically, the concept is you have a bunch of small computing units that are massively connected together. They were, I guess the concept was inspired by a brain where the little computing units are called neurons, and roughly compared to, I guess, a neuron in a brain, although I think the brains are a lot smarter than the neurons that they use in computing. And basically these computing elements have one output and multiple inputs. And associated with each one of these inputs is a weight. And what the computing unit does, it takes an input and multiplies it by the weight, and does that for each of the inputs, and then adds them together. And then it takes the sum that it gets and uses some sort of nonlinear function to generate the output. So the nonlinear functions are important, and doesn't seem to make a lot of difference exactly what they are. One of the simplest nonlinear functions is kind of a threshold, where the output is either a 0 or a 1, and as long as the sum that it generates is less than some threshold, the output is 0, or as long as the output is above the threshold, it's a 1. That's the simplest nonlinear function, I guess, that's used. The other variation of that is that it has 3 values, -1, 0, and +1. For certain type neuron networks, they want to be able to differentiate the output, and obviously the differential or the slope of an output that looks like that is not available. You can't differentiate it. So they use what they call a sig mode, I think is the way to pronounce it. It's basically kind of a smooth S-shaped curve like this, so that when you're near 0, it's more or less linear output, and it gets compressed to 1 or -1. And I guess the other thing that determines how these things are hooked up, or what you call them, is how they're interchanged or how they're interconnected. And I guess one of the most common configurations that I've seem to have found is they have a row of input units or nodes. They don't usually, there's a row of inputs, and then there's usually another row that they call hidden units. And then you got a third row, which is the output units. And the output for a full, what they call feed-forward network, the output from each one of these inputs, each output goes to every one of the hidden inputs. So you have a massive connections where each input goes to each of the hidden units along, and then the same thing is true from the hidden units to the output units. And so that's one of the most, I guess, simplest or most common arrangements. And on the strictly feed forward, all of the signals go from basically the first row to the second row and then to the output. And there's no cross connections. or a more complicated one, particularly the output from one will go to its neighbor or somewhere across. Now why do you have this kind of architecture? There's basically, I think, two reasons for pursuing this concept. One is, like I said, it's inspired by the brain, and so there's an effort to kind of try to understand what the human brain or an animal brain is capable of doing by building a model using these neural networks approaches. One of the neat things about them is what they compute is not so much controlled by the connections, but is by the weights. And so to program a neural network, what you're really doing is changing the weights associated with each one of these neurons. And they usually have some sort of algorithm that allows it to come up with the weights by trial and error or examples. And in other words, the network can learn to program itself by basically examples. I think the first one of these networks that was built was, I think, in roughly the 50s. And I think it was called Percepticon. And basically what it was, or what it did, is that they supplied it with a letter on a card. They had a photosensors, and I don't know exactly how many they had, but they would show the sensors the card with a letter written on it, and then they had 27 output or 26 outputs. And by showing it the output and then telling it, you know, it would give an output which letter it thought it was. And then they'd either tell it you're right or you're wrong. And they did this over and over again. And after each try, it adjusted the weights associated with each of the inputs. And eventually it got to where it could do a fairly good job of recognizing the letters. From what I have read, I don't know whether from a practical standpoint, but at least a laboratory effort. Somebody built one for the post office that would read zip codes, and it was, I think they achieved something like a 95% accuracy on handwritten zip codes.
That's what I get today.
Is that what you get today?
Yeah, with my local post office. 95% of the time.
Well, you know, and it has multiple layers. I mentioned the three-layer approach. Well, this one for the post office, they looked at little areas, and there was about, if I remember right, something like 6 or 8 layers of these networks. Then it seemed like one of the big problems is how do you program, how do you teach them? And there's two things involved there. One is called supervised learning, and the other is unsupervised learning. And the supervised learning is you give it an input, and you tell it whether the output was correct or not. And then there's an algorithm that goes and adjusts all the weights. And apparently that's a little bit of a black art to try to get it to where it'll learn fairly fast, and yet you don't want it to learn all your examples exactly, because you want it to be able to recognize examples that are, cases that are not original input. So